Hey guys, yeah, we're down here.
Thanks.
Alrighty. So today we're going to begin the journey of connecting all this geometry we've been talking about to the physics of amplitudes. Let me just remind you quickly what we talked about. Last time I defined the positive Grassmannian and that was the space of, you can think of it as a space of k by n matrices C alpha A. So this is k and columns. But with a positivity requirement that all of the minors, CA1 through CAK, that I'll sometimes abbreviate just by listing the columns, A1 through AK, is positive, greater than or equal to 0, when the columns are ordered. Okay, and so this is a Grassmannian generalization of a simplex in projection space. So if I call this G plus Kn, G plus 1n is just the simplex in Pn minus 1. Okay, and we motivated a second property. So you should think of the positive Grassmannian as the Grassmannian version of the simplex. It's curvy. That's what we stressed last time. So it has curvy boundaries. It has this very intricate facet structure because we can't just willy-nilly put minors to 0 in any order that we like because they satisfy Hooker relations. Okay, so that's the algebraic way of saying why there's some richness to the boundary structure. So it's much more interesting than simplex, and we're going to spend quite a bit of time understanding the boundary structure. And the motivation will start becoming apparent today. The boundary structure of the positive Grassmannian is in one-to-one correspondence with every on-shell process you can draw for n equals 4 superangles. Okay, so that's not supposed to be obvious at the moment, but it'll become obvious as we go along. So all the boundaries of this guy have some important physical interpretation. When we establish the connection. But it is something like a curvy version of the simplex, and associated with it is a certain canonical form, omega kn. So there's a canonical form for the positive Grassmannian, which remarkably has the property that it has logarithmic singularities on all the boundaries of the positive Grassmannian. We'll understand this more, why this is true, as we go along. But we saw in a couple of examples last time. In any case, we could guess what the answer had to be without doing any work. If it did exist, this canonical form looked like there's bkn c mod glk divided by the product of all the cyclic minors. Remember that we saw that the codimension 1 boundaries of the positive Grassmannian were when the cyclic minors went to 0, right? And if we just draw the picture, just to remind you, the picture for G3n, so remember, this is a picture where we sort of imagine we have a configuration of three-dimensional vectors, but we can slice it to get a two-dimensional version of it just by taking my configuration of three-dimensional vectors, looking at the rays coming out of all of them and intersecting with some plane, just to get a picture we can stare at. So then positivity just means in this two-dimensional picture associated with it, again, these are really, there's some origin here, there's some vectors in different directions, okay, but I've sliced it with some plane. And so if I forget about the rest of the three-dimensional picture now, the positivity here meant that the polygon had to be convex with this ordering, 1, 2, 3, 4 up to n. And we could see why the consecutive minors mattered, because I can't just go to a boundary where I set the minor 1, 3, 5 to 0. If I take 3 and I try to move it to be on the line 1, 3, 5, before it gets there, it will be on the line 2, 3, 4. Okay? So the first boundaries are just when 3 of the points become collinear with each other. Okay? Despite the fact that I didn't say that in the definition, I just said all the minors are positive. Nonetheless, it's kind of an emergent property that the first boundaries that you encounter are just when k consecutive guys become coplanar. Okay, so and therefore, if any such form exists, the only poles that it could have would involve the k consecutive minors, and then you just write them all down and you're done, right? You write this down, it has already the correct weights to be the right answer. I can't have any more poles downstairs, so if it works at all, this is the answer. Okay? And the miracle is that this is the answer. Okay? And I stressed a couple of surprising features of it, but in general, you see there's only n poles downstairs, but the dimensionality of the space could be much larger than n. Remember the dimensionality of the Grassmannian of GKN is k times n minus k. So in general, the dimensionality could be huge compared to n. Nonetheless, what happens if you start taking residues of this form is you find that on the support of some of the minors vanishing, the other minors factor into smaller pieces, and that allows you to keep taking more and more residues for this whole thing to make sense in the form of logarithmic singularities. Okay. Well, I have a lot more to say about this later, but just for now, you just have to believe me that if it exists at all, this is what it would have to be, and then we'll come back and understand better why it makes sense. Okay. That was a review of last time, but now what I want to do is go back and start making connection with physics. And to do this, we're going to go all the way back to lambdas and lambda tildes. So let's go back and think about the back to physics. So imagine that we have some lambda A, I'll use different indices, capital A and capital A dot. We're going to have a lot of indices floating around. So, okay. And if you remember from quite a long time ago now, there's a very nice way of just thinking about this data. Very early on in the course, I gave you a foreshadowing of the Grassmannians to come by just telling you that you can actually think about this data of the lambdas and lambda tilde as specifying some two planes in n dimensions. Okay? So let's just go through that again. So let's say you give me all the lambdas. So here's lambda 1, lambda 2, up to lambda n, that I'm grouping into a 2 by n matrix. And of course, our usual way of thinking about this 2 by n matrix is as columns, A1, A2, A1, B1 up to AN, BN. But what we did before is to instead think about them as two row vectors. So think about this one giant row vector, this is another giant row vector. And so in an n-dimensional space, we would have some giant vector A, some other giant vector B. Okay? And now what happens if you do Lorentz transformation? In a different frame, remember Lorentz transformations act as SL2, so in a different frame, you won't have the same A and B anymore. You'll have some A prime and some B prime, right? So on some different Lorentz frame, I'll have some A prime and some B prime. But there is something that's invariant. What is invariant? The thing that's invariant is the two-dimensional plane that's spanned by A and B. And that's because A prime is just some alpha A plus beta B. B prime is some gamma A plus rho B. Because this is a general SL2 transformation, right? Where alpha beta gamma rho was my SL2 of Lorentz acting on lambda, right? So that's really cool. The Lorentz invariant content of the data is giving a two-plane. Right? So you give me a two-plane in n dimensions. So here's a two-plane in n dimensions lambda. And some other two-plane in n dimensions lambda tilde. And we drew them in this way that they're orthogonal to each other because that's what momentum conservation is, right? Momentum conservation is the statement that these two planes are orthogonal. Momentum conservation is the statement of sum over A, lambda tilde A. 0, which just says that any vector in one plane is orthogonal to any vector in the other plane. Okay, so now we want to return to this picture. And so let me draw it a little more, so we have a little more room. And by the way, remember how important this picture was even for three-dimensional kinematics, right? This is what told us that three-dimensional kinematics have to be special. If the lambdas were generic, the lambda tildes have to be parallel, and vice versa, and so on. So, okay, so what do we have? We have in this n-dimensional space, we have a two-plane that will just collapse to looking like a line, lambda. And we have another two-plane lambda tilde. And we're asking them to be orthogonal to each other. And so you see this is kind of a fancy constraint. This is a quadratic constraint on this external data. As I emphasized at the end of last time, we're now going to make a lot of mileage by thinking about momentum conservation. And it shouldn't surprise you we're going to get mileage out thinking about momentum conservation, because momentum conservation is exactly the thing which is the most obvious thing in the world when you have the inside of a space-time. When you have local quantum fields and the inside of the space-time, it's blindingly obvious you have momentum conservation, because what is it translating? It's translating points on the interior of space-time. If you don't have the interior of space-time, which we don't when we're trying to do this entire project that we've embarked on, then it's not going to be so obvious that you have momentum conservation. So it's reasonable that momentum conservation is going to be something you have to think about. So we're going to think about it, and often in physics, when you have a nonlinear constraint, it's useful to linearize it so much as you can. Okay? So what we're going to do is instead of saying, so the obvious thing we say is that every single object we have in the world has a delta function associated with momentum conservation, if we're talking about amplitudes. Okay? That's the normal thing. So we just write that down, and then it multiplies whatever else is going on. We don't want to do that, because that's directly imposing this quadratic constraint, mixing up lambda and lambda tilde. So what we want to do instead is introduce a third actor into the problem. And of course, this is not how these things were discovered. Okay, this is some after-the-fact interpretation. They were discovered by experimenting and running into things and being confused for a long time and gradually seeing that this is what was going on. So don't think you're supposed to have these. This is supposed to be some super obvious thing. It's not super obvious, but it's a nice interpretation for what's going on. We say instead of saying this, let's say that there's a third actor in town, which is some k-plane. Okay? Actually, I'm going to now call it k-hat plane. Remember, I'm going to put these hats, we talked about it before. Later, we'll write k-hat equals k plus 2. Okay? So k-hat is going to turn into the number of negative helicity gluons, et cetera, et cetera. Okay? So it's going to be a k-hat plane. We don't know any of this yet. Let's call it c-hat. C hat of K hat. And what I'm going to ask, instead of saying lambda is orthogonal to lambda tilde immediately, I'm going to ask that C hat of K hat should contain lambda, that two-plane, and that separately C hat, K hat should be orthogonal to lambda tilde, two-plane. Okay? So clearly, if I can do that, it's going to force lambda to be orthogonal to lambda tilde. But I've sort of linearized the problem by introducing a third thing in the middle that has a relationship to lambda and separately a relationship to lambda tilde. Okay? So far so good? Okay. Now, let's just think a little bit just about this geometry. In general, let's just complain immediately. You say, look, this statement can't really make sense. For example, what do I do if K hat is a point? If K hat is 0, it can't contain the lambda plane. Or if K hat is 1, it can't contain the lambda plane. Okay, so whatever this picture is has to give us 0 when K hat equals 0 or 1. Right? So this doesn't exist for K hat equals 0 or 1. Right? Well, that's not so bad if we remember about amplitudes, which also vanish when K hat was 0 or 1. Okay?
Did you say the lambda plane contains C hat, or is it?
No, C hat contains lambda. Okay, I want C hat. In general, it's going to be a K plane with K bigger than 2. But I'm already saying if I make that claim, there's something wrong with K hat equals 0 or 1. Okay, that whatever I do just doesn't make sense. I'm going to get 0. But that's not so bad because we happen to know those amplitudes vanish. Okay, if we're interpreting them from something to do with amplitudes. Okay, so this is maybe okay. Another one is it seems to break parity between lambda and lambda tilde. Right? What about the symmetry between parity, interchanges lambda and lambda tilde? This statement seems to treat lambda and lambda tilde differently, but not really, because it's a perfectly symmetrical statement which says about the perps of these planes, right? So I say that C perp, which is n minus k dimensional, should be orthogonal to lambda, and C perp, which is again n minus k dimensional, should contain lambda tilde. Okay?
K or K hat?
K hat, I'm sorry. This is the first time in my life I've interchanged K with K hat everywhere in this lecture compared to what I normally do. So I hope I keep it straight. Okay, so that's fine. So this is in fact exactly the interchange between C of n minus k, C of K hat, and C of n minus K hat. Remember we said that's exactly a symmetry of the Grassmannian, right? I can switch between K planes and n minus K hat planes, and that's exactly just raising and lowering indices. That's the obvious duality. Okay, so this is not so obviously dumb. Okay, so let's keep going and try to write this picture in equations. Okay, so let's just try to put some equations associated with this picture. All right. So let's do the easy part first, that C is orthogonal to lambda tilde. Okay? So that means I'm now going to write down a formula with some delta functions, right? I want to impose these conditions. So C orthogonal to lambda tilde means that I should write down a factor as the product over alpha delta squared of C hat alpha A lambda tilde A. Product of alpha equals 1 to K hat. All right, that says that every single row, all the C's are just orthogonal to lambda tilde. So I'll abbreviate this as delta 2 times K of C dot lambda tilde, C hat dot lambda tilde. Okay? This second one is a little more interesting. C contains lambda. So what does C contains lambda mean? C contains lambda means that it should be possible to take some linear combination of the rows of C such that they equal lambda. So it doesn't mean that if you give me C itself, the top two rows will equal lambda, because I may not have recognized it yet. So I should allow myself the freedom to take linear combinations of the rows of C and to lock one to equal lambda. So what I should do is just integrate over all the linear combinations I can make. So I'm going to call the linear combinations rho alpha A, C alpha A. Okay, so there are k rows, and rho has the same index as lambda A. There are two of them, right? So it's going to run from 1 to 2. Okay? And so what I want to do is see, is there some combination, is there some row such that this is equal to lambda A? So I want to be able to find a row which does that. And so what I should put, then it's just, again, a delta squared of this, but now I have to integrate over all the rows. Oh, I didn't realize there are sums of rows and there are row variables. Great, very nice. Okay, so what do we have so far? Well, so we're done. Let me just write it down again. We have the product. We have the product over alpha. So we have this delta 2 times k, C alpha A, lambda delta A. Write it explicitly. And this integral okay. Now, let's ask, so are we done? So this is somehow imposing the constraints that C contains lambda and the C is orthogonal to lambda tilde. Well, we have to make sure that whatever the statement is actually a statement about the k-plane C. Right? So that means that when we do any linear transformations, we should get any k by k linear transformation on the C, this formula should remain invariant. And it clearly does under all the linear transformations with determinant 1. Because all those delta functions just pick up Jacobians that are all just the determinant, and this is all 1. But we have a little fly in the ointment, which is what happens just under the overall rescaling. So let's see what happens when I just rescale C alpha A, some overall T times C alpha A. Okay? So that's the sort of GL1 part of the GLK. And let's see what happens to this. Well, this guy, so if I do this, it's natural to scale rho oppositely. So rho alpha A will go to T inverse rho alpha A. And so from here, I pick up a factor. From here, I pick up a factor of T to the minus 2k. And from here, I also pick up a factor of T to the minus 2k. The minus sign because it's a delta of T. C is 1 over T delta of C. Okay? So this thing is not quite invariant. We have picked up an overall weight of T to the minus 4k. All right? So what are we going to do to fix that? Well, we're going to say, let's say in addition to these lambdas and lambda tildes, all the external variables are also accompanied by 4 Grassmann variables, eta tilde. And we're also going to write down the formula, the product over alpha, delta 4, C alpha A, eta tilde A, some I. So the only purpose of this is to make sure that we have something that's well defined as a statement about k-planes in n dimensions, right? So it's actually invariant under GLK. And if we add this factor, then from this guy, because it's the Grassmann delta function, when I rescale C, I just pick up T to the plus 4k. The 4 there is because I'm declaring this I runs from 1 to 4. Okay, so that's my choice. I'm adding 4 variables per particle. And so the whole thing is now invariant. Okay, so we're motivated so maximal supersymmetry is motivated now from this geometry, from the desire to talk about this k-plane, rather to really have this be a sensible statement about a k-plane. we didn't have to do it this way. I could also say that anything I do with this formula, I just have to multiply by some power of some minor involving C so that the weight works out. I can also do that. Okay? But this is a way of sort of packaging every such object together in one big generating function. So we don't have to, we could even take bits and pieces out of this delta function as we like, but this is the most symmetrical way of doing it. Okay, so let's see where we've gotten to then. Okay, so associated with this picture, and so now I should say that in addition to lambda tilde, I also have these super directions, eta tilde and lambda. I have that. Okay. Associated with this picture, I have this function. I have this interesting function of C lambda and C lambda lambda tilde and eta tilde. Now let's just think again. When k hat was 0, sorry, this is all k hat. Okay, when k hat was 0 or 1, this is 0. We can't do anything. When k hat is 2, when k hat is 2 is a very simple case. When k hat is 2, who is the k hat plane C? It's just lambda itself, right? So there's nothing to do. There's just sort of one thing that we can have. When k hat is bigger than 2, in principle, there are many planes that satisfy this constraint. Okay, so we have no canonical way of choosing one plane or the other, so we should sort of integrate over the space of all planes somehow. Okay? So in general, there's no canonical choice for what this plane is. So I'm going to define an object, kind of a formal object for now. I'll call it ln k hat, which is some integral of some measure on the Grassmannian, okay, times that function, times this thing. So I won't keep writing it down, I'll abbreviate it as this picture. Okay. Now, it's not going to surprise you, given everything that we've said, that we're actually going to soon choose this form that we're integrating to be the canonical form of the positive Grassmannian. Okay? But for the moment, let's not say anything about what it is. Well, actually, let me say it right now. Okay, so I'm going to say this is omega k hat and n. So let me make a few claims first. Okay, so this ln k hat, it depends on lambda and lambda tilde and eta tilde. Okay, it's some integral. I'm being a little loose because I have to tell you where I'm doing this integral. So in principle, it can also depend on where I'm doing the integral, how I'm doing the integral, the cycle on which I'm doing the integral. But let me not be too precise about that right now.
While you're erasing that one, oh,
Sorry, yes.
sorry. Just to be clear, I think I blinked and I missed it. Eta tilde transforms to t squared eta tilde.
No, eta tilde doesn't transform at all.
Okay.
Just c goes to tc,
Yes.
but delta, the Grassmann delta is just delta of eta is eta, remember. So delta of t eta is just t delta of eta. Okay. So that's this is the usual way that both that things cancel in supersymmetric theory. Yes.
So lambda is a plane and C has to contain them.
Yes.
I'm saying that C is a plane. How can there be a lot of possibilities? Like how can there be
Plane, there's lots and lots of planes that contain this two planes. It's a higher dimensional plane. Imagine you have a 17-dimensional plane.
Okay.
It can contain many ways it can contain a
Okay, so C is higher
two
dimensional.
plane. Yeah, K can be bigger than 2. Okay. All right. So let me actually define this to be the form on the positive Grassmannian. So okay, so this is dk hat times n c hat modulo gl k hat, and then all of these minors 1, 2 up to k hat, and 1 up to k hat minus 1 times this picture. It's just the formula that we wrote down.
Now it's just C hat, K hat.
Okay, but let me now make a few claims. So claims. First, before getting down to any details, there's something really startling and sort of amazing, that this picture makes all the symmetries of n equals 4 super-Yang mills completely obvious. We're now going to see conformal and dual conformal invariants just as obvious properties of this formula. Both at the same time, right? So, claim number one is that if I transform this to twistor space, so let me transform to a twistor space by looking at d squared lambda e to the I lambda u tilde, ln k hat, lambda lambda tilde, and eta tilde, that this is actually going to be the integral, measure on the Grassmannian doesn't change, but here what I'm going to get is something beautifully, obviously conformally invariant. In other words, in twistor space, ordinary twistor space, this is just going to say that C is super orthogonal to the twistor variable W. Okay. So where W, A is mu tilde A, lambda tilde A, and eta tilde A. So this makes obvious the SL4/4 of ordinary conformal symmetry. Okay? And actually, interestingly, for this statement, this measure did not matter at all. I could have this be any measure on the Grassmannian, and anything on the Grassmannian would give me something superconformal invariant, ordinary superconformal invariant. Okay. So for this statement, I could actually put any measure on G hat, K hat, N. And in fact, you can prove, it's been proven with some caveats, that every superconformal invariant of these variables can be thought of as an integral over a Grassmannian in this way. So this is not just some of them, all of them have to be expressed in this way. But two, there's a second statement, which is that Ln k hat, now of lambda, lambda tilde, and eta tilde, is actually, and we'll motivate this by saying, look, C contains this two-plane lambda. Let's just make it obvious that it contains the two-plane lambda. Since it contains the two-plane lambda, it's really dumb to just say you're integrating over all of these k hat planes. We just want to integrate over k minus 2 planes, right? Because there are clearly two of the directions are going to contain lambda. So if you do that, we're now going to see that you pull out momentum conservation, you pull out supermomentum conservation, you pull out the overall Park-Taylor factor, and then what's left is an integral over k-planes in n dimensions with exactly the same measure, but with a delta 4k slash 4k C dot the momentum twistor variables. Okay. Sorry? Oh, sorry, yes, it's meant to be eta tilde. Where these are our friends, the momentum twistor variables, mu A, eta A, with the usual relationship that lambda tilde A is A minus 1A, mu A plus 1, plus cyclic, over A minus 1, A plus 1, and similarly for eta tilde A, expressed similarly in terms of A's. Okay. For this statement, for the second statement, it is crucial, and in fact unique, to use this form, the form of cyclic minors, for this to be true. And we'll see why in a second. But I just want to pause here to say, again, stress how remarkable this is, because we just see purely, and we'll derive these things very simply in a second, we see just purely from the geometry, we've decided to think about momentum conservation in this interesting new way, and immediately we're rewarded by seeing that whatever we build from this picture will automatically be conformal and dual conformal invariant. Okay? That's exactly the thing that seems impossible from any local picture of space-time physics. These are two symmetries that are local in completely different spaces, right? This position space and momentum space. And yet here we are. Both the things are sort of falling out of exactly the same basic object. Okay, so now what I want to do is show both of these statements. But any questions so far? Is the claim clear? Yes.
So when you write out those intervals, should you have like GLK, like a gauge fixing?
Yeah, that was in my measure. So sorry, there's a mod GLK. Sorry, there's a mod GLK hat. Thank you, and a mod GLK. And of course here and here as usual, K is equal to K hat minus 2. Okay, so let's now establish these claims. Let's start with the top one, because the top one is really easy. Okay, so let's look at this formula. We have these 2k rho delta squared rho alpha a minus lambda a, and then we just have this delta 2 times k c alpha a lambda tilde a delta 4k c alpha a eta tilde a. So these are just going to go along for the ride, and now I'm going to Fourier transform with respect to the d squared lambdas, all of them. Okay? So this is a very easy Fourier transform to do because the lambdas are constrained by a delta function. Okay, so what happens when I do this? I can do the lambda integrals, and lambda is equal to this, and I shove it back. So this is the integral d2 times k rho e to the I, lambda is rho times c. So I get e to the I, c alpha a, rho alpha a, u tilde a. And now I do the integral over rho, and that's just giving me a bunch of delta functions. So this is just the product of delta squared c alpha a, u tilde a. Okay? So therefore, that combines with the rest of the delta functions, so the whole thing is just equal to delta 4k and 4k fermionic ones of just C alpha A, the super WA. I don't know if I introduced this notation before. When you have delta in m/m, it just means you write the bosonic delta function to the fermionic delta function. Okay, so that's it. That's how we see anything I do with this picture. When I go to twistor space, it's manifestly invariant under SL4 by 4x4 superlinear transformations, and therefore it's conformally invariant and superconformally invariant. Okay. Yeah.
So the rho of the A, is it product over A there and over A in the?
Sorry. This is a product over all A from 1 to n.
And the same for the delta function.
Sorry.
Same for delta 2.
Here. Which one?
That delta function is the product, also product.
No. Yes, that's right. This is the delta for each A. Exactly. That's right. That's right. The product over all the A's. That's right. That's how I managed to do all of the things. Okay? So That was easy. Okay? So, and here you see it doesn't matter what measure you integrate over the Grassmannian, you're going to get something that's super conformal in there. Yes?
So all the k's should be k hats.
Yeah, all the k's should be k hats. Are there any? Sorry, I told you, and the c should be k hat. Sorry. Okay. Now let's do the more interesting part. Two. And I'm just gonna I'm not going to. You can do this like super rigorously by gauge fixing and doing I don't want to just spend the time doing it because it'll obscure why it's working. So you can go through either the book on the subject or some of the references contained in the book if you really want to do it, or you can do it yourself with all the gauge fixings correctly done super anally. But I want to show you why it's true. So for the second part, our motivation is we want to say, look, C we know contains this two-plane lambda. So let's just write it in a way that makes it manifest that it contains the two-plane lambda. We somehow want to write C in a way that looks like, let's say the top two rows are just lambda, and then the bottom two rows are something else. Let me not call it C hat. This is C hat already. Some big C hat and some little C hat. Okay? So this is 2 and now k. Just remember k hat minus 2. And so, of course, we'll have a GLK symmetry acting on this bottom row. But notice that if we do this, we're still not done specifying what C is, because of course I could translate C hat by anything proportional to lambda. So you kind of further want to impose some constraint, just so I've locked this to a particular form. The constraint you want to impose is just that C hat is orthogonal to lambda. Right? So I want to impose that C hat alpha A, this little C hat, alpha A, lambda A is equal to 0. Now, what does it mean to, so what is it that geometrically we want to do? What we're doing is sort of projecting the entire picture onto the subspace that's orthogonal to lambda. Okay, so let's just do that. Let's just first ask for every such projection that we can do, and then find if there's any particularly, nice one, if there's anything special we could be doing with these projections. So in other words, I want to find ways I want to project onto the space orthogonal to lambda, to this two-plane lambda. So let me do that by looking for some linear transformation, n by n linear transformation QAB, such that QAB lambda b is equal to 0. Okay? So that's just obviously some, in the n-dimensional space, this is some linear transformation that's going to map the lambdas to the origin. So then I can look at the complementary direction, and that's what I want to see. Okay, so for any such Q, I can define C alpha A, big C alpha A, to be my C hat, alpha B, Q BA. So this is the multiplication from the right by Q. And then it just manifests that this C alpha A, lambda A, will equal 0. Okay, so if I do this to this big K hat by a matrix, what does this matrix C look like? If it looked like this, then C hat times Q would look like, for 0 in the top row, and some little matrix C in the bottom row, and that little matrix C would be orthogonal to lambda. Right? That's what we've now done. So now we've made sure that this C alpha, I really should have put a hat on the alphas as well, because these things run from 1 to k hat, I'm not going to keep putting them on. Sorry. So I have that this C alpha A lambda A is equal to 0. Okay. So this alpha now runs from 1 to k, not from 1 to k half. Okay, so any such projection gives me a way of doing that, right? And it gives me something which is orthogonal to a lambda. Now, with any such projection, I can also make momentum and supermomentum conservation obvious, because again, after all, lambda tilde should be orthogonal to lambda, right? So if I define, just as I did there, if I define lambda tilde A to be some mu B QBA, and similarly eta tilde A is some eta B QBA, then this will solve momentum conservation, right? And supermomentum conservation. Then I'll have lambda A lambda tilde A is equal to 0, and lambda A eta tilde A is equal to 0. Okay? Now, I should have said something earlier, sorry, before we got here, I apologize. I should have said the following, that back before I started, when we put C as, let's say I put it in this form, where's lambda C, then notice that some of the formulas we had before, remember we had a delta 2k of C dot lambda tilde, delta 2k hat of C dot lambda tilde, and we had a delta 4k hat of C dot eta tilde. What does this turn into? The top two rows turns exactly, the first one turns into momentum conservation, delta 2 times 2, the sum of lambda A lambda tilde A, and the next one turns into the supermomentum conservation part. Okay, so the top two rows are giving us momentum and supermomentum conservation. And then I'm left with the rest. I'm left with delta 2k now, not k hat anymore. Same C alpha A eta tilde A, delta C dot eta tilde, delta 4k, sorry, C dot lambda tilde, delta 4k, C dot eta tilde. Little c. Okay. And now, I want to solve them on the support of the momentum and supermomentum conservation, so I can certainly do this, right? Perfectly reasonable thing to do to make momentum and supermomentum conservation manifest. And if I do that, what do these things turn into? What's left? What's left turns into, I get a delta, well, first I have to remember that my C, I've chosen this representative so that it's orthogonal to lambda already. Right, so that was just sitting there already, right? This is we already have chosen to make sure that this little c is orthogonal to a lambda. Okay, but now let's see what the rest turns into. This is C alpha A. Lambda tilde A is like mu tilde B QBA. Right? Now this almost looks like it's our, oh sorry, I'm really sorry. When we did this, I have this little c hat. This is the matrix that we're talking about. Okay? So everywhere here is the little c hat. Everywhere in here is my little c hat. Okay. So you'll notice that if I choose, let's forget about this. Just manipulating those the delta function. If I choose QAB, choose QAB to be symmetric, QAB equals QBA, then I can invert this here, and this becomes C hat alpha A to AB mu B, which now becomes that little c alpha A, alpha B, mu B. So this is the natural thing to want to do, right? We want to be able to go back and forth. Yes?
Is it obvious that you can also
No,
always make this choice?
Oh, we're going to make it in a sec. Okay, we're going to show how to do it explicitly in a second.
Okay.
But I just want to say that we don't have to do this. But if we can manage to do it so that Q is symmetrics, then this thing turns into that. All right. Now I can do what I wanted to do. So now, and remember, this C is also orthogonal to lambda. This little c is now orthogonal to lambda. So now let's see what we know about this little plane C. This little plane C is orthogonal to lambda. But also we have that C is orthogonal to mu. Right? Well, we're imposing that. Now this is a condition that we're imposing. And the same for the etas. So if we can do all of this, remarkably, we appear to get something that has a dual conformal symmetry. Okay. That's grouping the Z, grouping this lambda, mu, and eta into a super Z. Okay, but there's a little fly in the ointment. I'm saying that I'm doing this so far just so you see why you even dream of something like dual conformal symmetry, right? Why would you even think there's anything like it? From this, once you're in this world with this picture of these planes, you immediately see conformal symmetry. You want to say, oh, I'm integrating over planes, or they contain this two-plane. Let me just make it obvious that it contains the two-plane. And then as you do it, you see, wow, the conditions look like they want to be invariant under another conformal symmetry, right? But this transformation that we do, remember, this transformation is designed to kill lambda. So Q times lambda is 0. So Q will clearly depend on the lambdas, right? And so what is not obvious is that when I map from the C's to the C hats, I had a formula that was integrating over the C hat Grassmannian that involved minors of the C hat Grassmannian. But after I do this linear transformation from the C to the C hats, it's not obvious what the k by k minors of the big Grassmannian are going to do in terms of k minus 2 by k minus 2 minors of the little Grassmannian. Right? After all, we just have some big k by k minors and do a linear transformation where the entries are going to have lambdas in them all over the place. And now when I compute those minors, in general, I'll have some complicated functions of the lambdas as well as the old minors coming out. So that part of the answer, the measure of the Grassmannian part answer, may have lambdas in it all over the place. And that, of course, would totally mess up this conformal symmetry, this new conformal symmetry. Okay? So this is where the magic is going to happen with the form that has cyclic minors. Okay? So this thing with the consecutive minors, something magical is going to happen. And to do it, we're going to have to make also the obvious natural choice for Q. Okay? So let's talk about what all possible Qs are first. How do I come up with all possible Qs that annihilate the lambdas? Yeah.
So little c that you're writing right here that you're erasing.
Yeah.
That's when you multiply big C by Q and then take like the lower.
That's right.
part.
Exactly. Exactly. And I multiply the big C by Q after I put big C in a form where the top two rows contain lambda, the bottom k minus k rows are little c. Okay. So, well, in order to see what it is that annihilates lambda, let's remember again. The only thing we have is the three-term relation between lambdas, right? So I know that if I write down the formula, if I write down the formula of AB lambda C plus CA lambda B plus BC lambda A equals 0, that's the only identities that these lambdas satisfy. Okay? Now, that also is, well, that's That's if I think of a big vector, an n-dimensional vector. If I take an n-dimensional vector, let me look at this just a little more. It'll be nice in a moment, just for convenience. Let me write it like this. So the middle guy. And I'm going to write the formula. Just divide by. Now I've written it in such a way that this formula has the little group weight of B in it. Okay? When I rescale formulas, it does exactly the same. The little group of 1 over lambda. Anyway, okay. What this means is that if I take, so I'm going to, here's an n-dimensional vector, 1, 2, up to n, and if I just in the slots A, B, C, if I put exactly these guys, right? If I put, oops, this was 1 over AB. If I put 1 over AB, CA over AB, BC, 1 over BC, and zeros everywhere else. Okay? This vector, let me call this little q, A, lambda A is equal to 0, obviously. Right? That's just our identity. Okay? So I can make an n by n matrix that annihilates all the lambdas just by shoving these, every row has 3 of these, has 1 of these identities in it, right? In every row I just put these things in each row and I just write n of them. So that's the most general Q matrix, okay? The most general Q matrix we can have is some n by n matrix where every row has 1 of these 3 terms relations. I put them anywhere I like. And so on. Is that clear? But I want this matrix to be symmetric. If I want this matrix to be symmetric, yeah.
You could also do combinations, right?
Sorry, you can do combinations too. Yeah, we can take after we do this. We can take any linear combinations that we like. But this is a very simple canonical way of making this matrix. If we want this matrix to be symmetric, then the 3 term relations that we choose, if we want it to be symmetric in AB, it'll be guaranteed to be symmetric in AB if the 3 term relations that we choose are symmetric around B as the intermediate point. Okay, so if we do that, then the matrix will be symmetric. And given that consecutivity is so important in this entire story, right? Everything about positive, everything we've seen so far, consecutivity matters. By far the most natural choice is to just use these identities and involve 3 consecutive labels. Okay, so A minus 1, A, and A plus 1. So if I do that, so for every row, I just put 1 of the 3 term identities and I just slide them over. Okay? So that's the most natural choice. And that gives you a specific Q matrix. So the most natural choice, or a natural choice anyway, is to use the 3 term relations involving A minus 1, A, and A plus 1. And so concretely, that the QAB matrix is just delta A minus 1 and B, A plus 1, plus delta AB, A minus 1, A plus 1, A plus 1, A minus 1, plus delta A plus 1B, A minus 1A over A minus 1A, A plus 1. And so that's a symmetric matrix now that's guaranteed to annihilate lambda and is somehow the kind of most natural thing I can do. All right, but now comes the real magic. Let's go back. Now we're going to see the magic of cyclic minors. So let's go back to our C matrix. This is now C hat matrix, sorry, which was lambda upstairs and this little C hat downstairs. Okay? And we know that what goes in the measure of this guy are the K hat by K hat minors. Okay, so let's look at the K hat by K hat minor of this matrix. So let's look at this minor 1, 2 up to K hat. So this is just this determinant, which is lambda 1, lambda 2, lambda K hat minus 1, and lambda K hat, and the C hat. Just the C hat 1, C hat 2, C hat K hat minus 1, and C hat K hat. Sitting down there. Okay? Now, what is the minor of this matrix? Something complicated, right? It's, for example, this little determinant times that K hat minus 2, K hat minus 2 minor. And then plus that one times the complementary one, plus that one times the complementary one, right? It's a big sum of determinants involving the little 2 by 2 determinants made of lambdas, which are our friends, the brackets, and some of the minors out of C hat. That's exactly what we said. No reason that it looks simple, doesn't look simple, it looks complicated. Okay? But you learned something probably you're too young. But when people actually multiply things out by hand back in the Stone Age, if you want to compute determinants, there is a fun thing that you can do. For example, if I wanted to compute this determinant, one nice thing would be to take linear combinations of the columns to make that 0. I can do that, and the determinant is unchanged up to some overall factor, right? That I can work out. I can just take linear combinations of the columns, set that to 0, that to 0, that to 0, that to 0. Okay, and of course I can't set them all to 0, because the determinant isn't 0, but I can certainly take linear combinations between, and what's the most natural thing to do in this case, between adjacent columns to set these things to 0. Now just think for a second, what linear transformation am I doing on the columns when I'm doing that? Exactly Q. That's exactly what we're doing, right? It's exactly Q, which is telling you to do a transformation, to take this one and add a linear combination of its neighbors. Okay? So I can do that to set all of these things to 0, but for the ones on the outside. Okay? Is that clear? So under the action of Q, this is going to go to some lambda 1, which I didn't touch, lambda K hat that I didn't touch. I put everything to 0 in here, but who do I have down here? It's just C. And therefore, we learned the following wonderful fact, that the minors 1, 2, K hat minus 1, K hat of C hat is actually equal to some factor, which I'll write down in a second, times these minors 2, 3 up to K hat minus 1 of C. Okay?
Why does Q leave lambda 1 and lambda K hat?
No, because I'm not even touching those. So I'm just doing a linear transformation here, just to change this guy and that guy and that guy, because this has neighbors. All of these guys have neighbors, so I can shift them by their neighbors to set them to 0. This guy does not have a neighbor here, so I'm not touching it. Okay, so I'm just doing this I'm just taking this column and I'm shifting it by relation by the correct amount with its neighbors and set it to 0. Okay?
What if its neighbors are linearly dependent?
Sorry?
What if they're
I'm assuming for the then this minor it could vanish, but I'm assuming that the lambdas are generic for the moment. Okay, so and we'll even see that in the structure of the answer. That assumption in the structure of the answer in a second. Okay, so yet another way I could have motivated all of this is to just go back and do this. Say, look, I have this complicated k by 2 by k by 2 minor, k hat by 2 by k by 2 by k plus 2 minor, but it's natural to do these linear transformations of a guy shifting with his neighbors to set all the intermediate columns to 0, and if I do that, the big k hat by k hat minors are proportional to a small k by k minor, and that linear transformation is exactly this cube. Okay. Now you can work out this constant of proportionality, and it actually just ends up being 1, 2, 2, 3, up to k hat minus 1 k hat. Just these minors made out of the lambda hats. So with that magic, we're done. Right? Because now we have a formula. Now the kinematic part that forced C to be orthogonal, C hat to be orthogonal to lambda tilde, and all the kinematical part that we saw just turned into C being orthogonal to the to Z, the momentum twistor Z. That part is just what we had before. And also the measure with the form with cyclic minors turns into the form with cyclic minors on the smaller Grassmannian, just from the simple linear transformation. The only thing that's sort of left to work out is some Jacobians from some of these cases of variables that we did, but when the dust settles, there's not that much dust, we literally get this formula that we already pulled out. We pulled out momentum conservation. We pulled out supermomentum conservation. All the rest of the stuff collapses into this one part Taylor factor. But it's sort of obvious that it had to, because the only things that are involved are brackets involving lambdas, and this is the only expression that has all the right weights. Okay, so but now what's left is exactly this integral over k times n little c mod glk over the little minors. Okay. And as promised, this manifests dual conformal invariance. All right, any questions about this? Yes?
So we said before that the momentum twistors make momentum conservation manifest.
Yes.
So can we get rid of the delta 4 using those variables?
Well, that's exactly what we did, right? We wrote the lambda tilde and the eta tilde in terms of these mu's and etas to do exactly that. But we started off with this, that's what I'm saying. We started off with this object whose purpose was to make momentum conservation obvious. So let's summarize. We started off with this picture where we think about lambda and lambda tilde as two planes in n dimensions, and they have to be orthogonal. We tried to make that statement obvious by introducing this auxiliary actor into the game, this k-plane in n dimensions, and asked it to contain lambda and be orthogonal to lambda tilde. The mere statement of those facts gives you an object that first, to make it really a statement about k-planes, we have to make it supersymmetric. That's already, and if we want to do it in a way that respected all the cyclic symmetries of the problem and so on, we made it supersymmetric. Then that mere statement of the k-plane containing lambda and eta tilde, containing lambda and being orthogonal to lambda tilde and eta tilde, in ordinary twistor space is obviously invariant under k by k linear transformation, so we see superconformal symmetry. We come back to where we started with lambdas and lambda tildes, and we say, okay, we've made momentum conservation obvious, but let's make it manifest that C contains this two-plane lambda. I'm not really integrating over all k-planes because the damn thing has to contain a two-plane. So you just make that statement geometrically obvious and you follow your nose. You try to make that statement geometrically obvious, and then you discover that you can write that object in this way, where indeed we factor out. We made, as hoped for, as was part of the point, we made momentum and supermomentum conservation obvious. But the integration over the space of all k-planes now reduces us to exactly the same kind of object, but with k down reduced by 2, and discovering, notice that we discovered the momentum twisted variables. We didn't invent them. We sort of, they're handed to us by this linear transformation that shifted columns proportional to its neighbors in order to map the k plus 2 by k plus 2 minors down to the k by k minor. Okay? So we sort of discovered that this object is also invariant under a second conformal symmetry in the momentum twistor space. So, so that's so whatever we do with this picture is going to be something which is going to be obviously conformal and dual conformal invariant. Okay. But let me just, so starting next time, now we're going to start being much more, we're going to go back and being systematic and responsible. Well, let me tell you a little bit more about what it is that we're going to be seeing. So let me write both these formulas down again. And we'll see this in more detail starting next time. So we have this writing it again. The first thing we're going to have to figure out is what this integral means. Okay? And it's actually easy to see, it will be easy to see, and we'll see it starting next time, that these delta functions impose a lot of constraints so that in the end, the actual number of integrations we have left to do is not remotely as high as k times. This space is k hat times n minus k hat dimensional, but it's not remotely that high. Okay? We're going to be left, all these delta functions are going to leave us with a very specific dimensionality of space we've got to do an integral over, and it's going to end up being 2n minus 4 dimensional. So we have to find some 2n minus 4 dimensional, just if we want to get a number of it. Let's say we don't care to get a number. If we're happy to still have a differential form left, then we'll get a higher forms. If we want to literally get a function out of it, we have to find some 2n minus 4 dimensional set. Okay? If I write this as what we just did, delta 4p, delta 8q, this is just the recognize just the Mark-Taylor formula times this integral okay, here too, we're going to have to do the integral over a specific again, something of a specific dimensionality that will end up being 4 times k. Sort of obviously see that from the delta functions. So we have to find some interesting 2n minus 4 dimensional place to do this integral, and some interesting 4k dimensional place to do these integrals. All right. Now, the natural places to do these integrals are going to end up being on the facets of the positive Grassmannian. So, so we have the positive Grassmannian, which is the sort of top dimensional region inside the whole Grassmannian, but it has facets of lower and lower dimensionality. Right? Of all dimensionality, that's one reason we can talk about a canonical form associated with it. This canonical form is supposed to have logarithmic singularities on all the boundaries. And so all of these, in fact, there's something we can do with every 2n minus 4 dimensional boundary. But with boundaries of all dimensions, again, if we want to get numbers out of these things, we pick these 2n minus 4 dimensional ones. But the connection between this formula and the positive Grassmannian is going to end up being that on the one hand, cells of any dimension of the positive Grassmannian, remember we're trying to build matrices which have we're trying to build matrices where all the minors are positive. And on the one hand, we're going to learn that building those matrices, not just where all the minors are positive, but where some of them have, where some of the minors might be 0, so that we're going on boundaries, are going to be associated with drawing pictures like this. Okay? We're going to draw pictures with black and white vertices. So these pictures are going to be standing for two things. On the one hand, they're going to give us cells, quote unquote cells, or boundaries of the positive Grassmannian of all dimension. And they will have the feature that when we do this integral, so when I say I have to do it over these cycles, I have to take residues. So it's I'm going to I have to take residues to get down to integrals of this of the appropriate dimensionality. But when I do that, exactly these things are going to give me an on-shell process. Where what I would do is just take these 3 particle amplitudes of the 2 types that we have and just glue them together and integrate over the on-shell phase space of all the intermediate lines. So these are 2, on the face of it, totally different problems. Beginning next time, we're going to come back and just start with the physics motivation. So we're just going to start by going back and looking at the 3 particle amplitudes and just asking the question, what do they look like? How do I glue them together? And what kind of objects do I make when I do that? So that's already going to have a lot of interesting payoff, purely just playing with these things. We'll learn how to interpret BCFW recursion relations in this language, just drawing these pictures with black and white vertices. So there's a whole collection of objects of this sort that we'll get purely motivated from the physics desire that we start with the elementary building blocks, which are 3 particle amplitudes, but we glue them together without ever talking about virtual particles. So they're not Feynman diagrams. They're on-shell diagrams where everything is glued together so that everything is, all the internal particles are on-shell. So we'll just play for a little while and stare at these guys and learn that we can actually build the amplitude in terms of them. So it's not totally obvious, but we'll actually be able to build the amplitude in terms of these guys. And as we start studying them, we'll see they satisfy all sorts of very interesting identities between each other. You might naively think there's infinitely many of these things. So you could draw infinitely arbitrarily complicated on-shell processes. But we'll see, if you fix k and you fix the number of particles, it's not obvious, but there's actually a finite number of these objects you can ever talk about. Okay, so that's the first interesting thing, that the number of different functions you could possibly get out of this is actually finite. Okay, but one thing is just drawing these pictures purely from the perspective of physics, and you could do that for a long time and enjoy doing it and understand how to think about recursion relations and so on from this point of view. But the second surprise is that these things are literally in bijection with facets of the positive Grassmannian. And the connection is that it's literally the same picture shows up in both problems. We're actually going to discover it from the ground up. I've sort of gone to the end to tell you what the final story is. But we're going to discover this from the ground up starting next time by actually, after we just play for a little bit, gluing these 3 particle amplitudes together, we're going to ask how we can do this more systematically. Okay, how do we actually, we want to avoid the difficult work of doing the intermediate on-shell phase space. Because remember, momentum conservation is a quadratic constraint. So as we're putting everything on shell in the middle, it's going to become more and more of a pain in the ass to make sure that all the intermediate lines are on shell and satisfy momentum conservation. So what we'll do is go back and write the three-particle amplitudes in such a way where we don't have to think about momentum conservation by introducing some auxiliary variables. That's going to precisely be our favorite Grassmannian formula, just for the simplest case of k hat equals 1, n equals 3, and k hat equals 2, and n equals 3. Already in those simplest possible cases, we'll see the motivation for introducing this Grassmannian picture just to make the three-particle kinematics obvious. Okay? But once we do that, it'll make it much, much easier to actually glue objects together on shell and do all the intermediate phase space integrals trivially. But we'll then be left with all these integrations left to be done. And then after a little while, we'll recognize that those integrations left to be done are actually associated with a k by n matrix. And if we stare at it a little more, we'll see that this k by n matrix, with some judicious choice of signs, has all of its minors positive. And that'll be the sort of beginning of seeing how we go back from the direct, sort of responsible way of gluing three-particle amplitudes back to seeing this is actually associated with the Grassmannian. Okay? And some of this is special to n equals 4 super Yang-Mills, but some of the kinematical aspects are universal for any planar theory. Okay, so it has so some of it has to do with supersymmetry. A lot of it has nothing to do with supersymmetry. It just has something to do with planarity instead, at least for the connection with the positive Grassmannian. And so we'll start seeing that next time. But already, just playing with the on-shell diagrams gives you this connection between on-shell processes and the Grassmannian, and this particular form on the Grassmannian. And you could then imagine that things historically went in that direction. You study on-shell processes because you think they are interesting. You learn you can represent amplitudes in terms of them. You associate it with the structure of the Grassmannian, and then the structure has its own life. You see that it goes over here. It manifests these other symmetries, and so on. Okay, so the next number of lectures is going to be all about this subject: on-shell processes, the Grassmannian, gluing black and white vertices together, getting familiar with what the positive Grassmannian looks like, what its boundaries look like, how we think about these pictures as associated with facets of various degrees of the positive Grassmannian. And so you can think of and we'll see how all the terms in BCFW recursion relations are particular examples of these pictures. We'll see how we can think about BCFW recursion relations for n equals 4 super Yang-Mills, so all loop orders in this language. Okay, so I've deferred talking about loops till now because after we get this under our belts, it'll be a lot easier to talk about loops. Okay, so we'll do trees and loops to all loop order from this perspective. And after all this is said and done, we'll start zooming back out and asking the questions. If I never knew about quantum field theory, I didn't know about the derivation of these recursion relations, why am I summing these pictures together in a particular way? Right? And that will lead us back to the story of the amplituhedron. That will eventually lead us back to this picture that I summarized on half a blackboard a few lectures ago of this question we asked at infinity involving the winding of external kinematical data. So we're going to get back up there, but we're going to spend some time in the world of these on-shell processes to get used to another point of view. Okay, thanks a lot. We'll be back usual place on Thursday. Oh, yeah.